The problem from GATE Physics 2022 reads as follows. In Hall effect experiment on an intrinsic semiconductor, which of the following statements are correct? Option A. Hall voltage is always 0. Option 2. Hall voltage is negative if the effective mass of holes is larger than those of electrons. Option 3. Hall coefficient can be used to estimate the carrier concentration in the semiconductor. And option 4. Hall voltage depends on the mobility of the carriers. Now let's go ahead and start solving this problem and have a look at how does a typical Hall experiment setup looks like. So this is a semiconductor bar which is intrinsic. So what do we mean by intrinsic? When we mean intrinsic, we mean that the concentration of electrons is equal to concentration of holes is equal to the intrinsic concentration Ni. This expression is valid for intrinsic semiconductors. And a current I is flowing through this semiconductor because we have applied an external bias which is denoted by the potential Va. The field is applied in the vertical direction, that's the Z direction. We know that the Hall coefficient for an intrinsic semiconductor is given by this formula that's written on your screen, on the left of your screen. Now, we know that for an intrinsic semiconductor, N equal to P equal to Ni. Let's put this value here, okay? So, I'll get Ni mu h square minus Ni mu E square divided by E Ni mu h plus Ni mu E whole square. Now I can take Ni common from the top and so it will be mu h square minus mu E square divided by, I can also take Ni common from the bottom, so it will be E Ni squared, it will be mu h plus mu E whole squared. Now I can write this, Ni get cancelled, so I'll get 1 over Ni E. Mu h minus mu E whole square can be written as mu h plus mu E times mu h minus mu E divided by mu h plus mu E whole squared. 1 mu h, this gets cancelled, and so I get RH equal to 1 over Ni times E mu h minus mu E over mu h plus mu E. Now this is the expression that we get for an intrinsic semiconductor. Now note that in an extrinsic semiconductor, RH is simply minus 1 over Ne. And just by looking at this sign and by looking at this number N, we can, just by measuring the Hall coefficient, we can get the extrinsic carrier concentration. We can't do that here. Since RH is dependent on carrier concentration, intrinsic carrier concentration Ni as well as mobilities. So we just by measuring the Hall coefficient, we cannot simply get the extrinsic carrier concentration. We cannot get the value of Ni simply by measuring the value of RH. We also need mu h and mu E, and that's a complex exercise. So this is one thing we learned, that in an extrinsic semiconductor, Hall coefficient does not directly give the carrier concentration. Okay, now let's move forward. Let's do one more exercise. Since we are interested in Hall voltage, we know that RH equal to Hall coefficient is defined by this, and Hall voltage, this E Hall can be written as H Hall over the width W, and J, the current density, can be written as current I divided by W into T, the cross-sectional area of the semiconductor slab, times B. W and W gets cancelled, so we get V Hall times W divided by IB. This will give us as V Hall equal to RH times Bi over W, and I'll replace the value of RS that we obtained here. So I'll get Bi over W, right? And RH is 1 over Nie times mu h minus mu E over mu h plus mu E, right? So this is the expression for Hall voltage that we have obtained for an intrinsic semiconductor. Now let's move ahead with this expression, and let's try to analyze what can we say about the Hall voltage based on just on this expression. Now this was the expression. Note that Bi sorry, it will be, okay, so W gets cancelled, it will be T here. I'm sorry, so this will be T. So this is the expression that we got for Hall voltage. Okay, now, so you can clearly see that the Hall voltage being positive, this is a constant term, right? The Hall voltage being, it's not zero first of all. So Hall voltage is not zero. Why? Since typically mu H is not equal to mu E. So first observation we can make that. Now, is it negative or positive? So it is negative or positive, that will depend whether mu H is greater than mu E. So if mu H is greater than mu E, we will get a positive Hall voltage, right? It's as if that semiconductor, even though intrinsic, is behaving like a p-type because it's a positive Hall voltage. On the other hand, if we get mu H is less than mu E, this implies we will get a negative Hall voltage. But we cannot conclusively say just based on this expression that V Hall is positive or negative. However, if we are given in the question that mu H is less than mu E, this means if mobility of electrons is greater than mobility of holes, it's definitely Hall voltage, or vice versa. If we are given that it's a negative Hall voltage, then we can definitely say that the mobility of electrons is greater than mobility of holes. Now, one more thing, we know that mu E, or let's say mu E equal to tau E times m star, right? Tau is the relaxation time and m is the effective mass. Now, even if we know something about mu, we cannot say conclusively about effective mass m because the relaxation time is also there. So please note that even if you can conclusive, let's say even if you can see mu E is greater than mu H, that does not necessarily mean me is less than mh. Why not? Because the factor tau is also there. See this. Hence, even if we have a comment on the mobility, we cannot conclusively say anything about the effective mass, right? So let's go back to the question now, right? So we know that Hall voltage is always zero. No, that's not correct. We derived an expression where it was dependent on mu H minus mu E. So it's not always zero. Hall voltage is negative if the effective mass of holes is larger than those of electrons. That's not necessarily true. Remember, we told that it's the Hall voltage is dependent on mobility. Sure, mu E and mu H. But mu E and mu H itself depend upon the effective masses and the tau. So depending on what their ratio is, mobility is determined. So we cannot conclusively say whether it depends on effectively mass. So this option was wrong. This option is also wrong. Hall coefficient can be used to determine the carrier concentration semiconductor. That's not correct. Remember that Hall coefficient was something like dependent on Ni and some factor of mu H minus mu E upon mu H plus mu E. So you cannot directly determine the concentration just based on RH. You also need to know the mobility. So we cannot directly determine that. However, we know that Hall voltage, which is the expression which was dependent on mu H minus mu E over mu H plus mu E, we can determine this. So Hall voltage, this is the Hall voltage, was directly proportional to this. Depends on mobility of carriers. So option D is the correct here. Thank you for listening.